Started the recording, and let's get started. If somebody joins us, this isn't the display I want. There we go. So I'm recording. If you've got anything you want to ask, put it on the chat or something like that. But let's get going. Second webinar, focused on 3D metrology in the modern day engineering and manufacture. I said I'd help out here and do one of these. So a little bit about me first, I guess. I think you all know already, Sam, but for those that watch afterwards, I did my apprenticeship at Rolls-Royce here in Derby back in 1999. Seems like an eternity ago now. And then established in a role as a manufacturing engineer in Derby, working on turbine blades. I did a lot of jig, fixture and tooling design back then, before taking a little sabbatical and moving then afterwards to work at Bentley Motors in Crewe. It was an interesting year or so, but it kind of made me realize two things: that the car industry wasn't so much for me, and how I was quite keen to get back to Rolls-Royce. At the same time, the financial crisis hit, and so this gave the opportunity to look elsewhere. So yeah, I came back to Derby. I worked as a CAD/CAM specialist for a few years. This built on the NX knowledge and the jig and fixture knowledge that I've built up over the years, before taking a bit of a gamble, really, as a business metrologist. This is a role in metrology, measurement and inspection, which is still the industry I'm in today. So I did for just over 5 years there at Rolls, working on turbine blades, and then working more towards structural components. Started working in the supply chain. Started essentially doing development activities, looking to promote the use of metrology, looking at business cases. And I started working a lot with GOM Metrology. When I was ready for a next career step, I reached out to these guys and things just kind of snowballed. So yeah, I'm into my third year as of April this year. I'll have been here 3 years now. And the role is business development. So fundamentally, my role is to help coach, guide our global teams in the use of technology with predominantly the aerospace industry. So how we use metrology to help companies gain competitive advantage, reduce costs, and really to use this for the future. A very awful photo before I learned how to smile nicely, of my graduation. So yeah, this for me now is well over 10 years ago. I studied part-time when I was at Rolls-Royce. You see, there was no real gap there to do full-time study. So I worked my way through the BTECs, through the HNC, and then onto a bachelor degree at Nottingham Trent. So all of this was day release, mainly around mechanical engineering, completing that back in 2007. That's also the time that I kind of took this sabbatical. In terms of Whitworth, and yeah, I was an award holder throughout the studies for my degree. Became scholar after this. In 2012, got an invitation to apply to be on the committee. This led to initiating some activities like the newsletter, the social media, and so on. And very proud to be the visionary award holder in 2015, followed by the society vice president, and then the president just a couple of years ago. Before Howard took back over the role. My softer side, I guess, beautiful family there. You can see. So I got wife, 2 children. This was New Year's Eve this year. Taking them out for a curry. They're getting to the age now where we can have a little bit more fun past the baby years where they're extremely demanding, and we can do some nice stuff together. And then the fat lad. Drag myself around a triathlon. This is how I kind of get my balance between what's quite a hectic work and life balance. This is my release at the weekends and evenings. So a little bit about me outside of the profession. But I said I talked to you about 3D metrology. So first and foremost, sorry about the corporate slides. I'm a bit restricted actually. I use the work laptop all the time, and you would not believe that their PowerPoint version does not allow anything other than the corporate branding in the side. But actually, it's worked out quite well because our say introductory PowerPoint material is really good for an overview of just how 3D metrology is used and what that means to all of the industries. So a little bit about GOM. GOM is now circa 25 years old. It develops, produces equipment, hardware, automation, software, entirely focused around the 3D optical metrology solutions. Also just recently introducing CT, computer tomography, or X-ray CT, to its suite of offering. So this visual, just showing from the top left-hand corner, the snapshot of the software. Bottom left here, we'll learn in a second, is around the 3D optical metrology. This is 3D optical metrology in an automated environment on car bodies. Is in this example with standard solutions with automation built in, and then in the bottom right hand corner here our Aramis SRX system. So this is for 3D testing. So building on this theme of how we are really pushing the idea of 3D metrology in all aspects of engineering. So this should be a little video that plays now. So what you're looking at there is what we call a sensor, an Atos sensor, and it projects a light and a pattern there, often known as a fringe projection. So those flashes of lights combined with the 2 cameras, which you can see triangulating and pointing towards each other, are capturing multiple images in any 1 second. So you see the flash of light there. This was a very small object, plastic part for mobile phones, cameras, this type of thing. But the technology is really scalable. So here you see the highest end, the biggest of solutions that are on offer, with dual robot cells taking images at the same time, working in harmony, and in this case for the automotive. You can see from the software side now, this is a software image of the programming. You can see this also in the bottom right hand corner, which is entirely mimicking offline what's happening in the actual Atos scan box. So we acquire all that data, and then everything you see in grey there is the captured imagery. So we take all of those images, we combine them together, and we generate what we call a mesh. And in our case, it's a very high resolution mesh. We have extremely high resolution. Thereafter, you can do with it what you really well want. So you saw a color image there, which was a comparison to CAD. Now you're seeing what is quite a traditional measurement where people are taking points to analyze these against, say, drawings or functional dimensions in the very traditional way. But as people have become more and more used to the technology, they push us more and more. Okay, so things like character lines on cars here, we can pull out from the software, we can analyze these, whereas before this would probably only have been possible by a visual inspection. And what you've just seen happening there is the build-up of a virtual assembly. So this allows international companies like VW, for example, where they can measure parts for new products in all corners of the globe and build this together virtually based on the real data to do the analysis that they would like to do. So this is, I would say the latest technology, but also, it's also quite mature now, in terms of the technology. It's been around since the 90s now. We've just really pushed this on to, in a lot of cases, kind of replace the tactile, maybe CMM style measurements, or you see like articulated arms, Roma arms, things like this to do these types of inspections. We're super quick when we do this type of inspection. Being a 3D company, then the next natural progression for us was to move into X-ray CT. Unlike competitors on the market, this is really based on achieving really high accuracy. So we have a 225 kV X-ray source and a 3K detector. At the time of bringing this to market, this was by far the biggest, and this gives us what we need in terms of resolution and accuracy, and that's really what we would pride ourselves on, and what customers have become to expect of a GOM product. So this is again how we can then gather this 3D information to change the way people look at design and manufacturing in the future. And also to kind of complete the suite of 3D products that we've got 3D testing. And for all of us that have been through the kind of mechanical route, where it's very standard in the early days to perhaps do a tensile test on a specimen, measure the cross-sectional area afterwards, and so on. We take that to a new level. So here you can see a similar principle here. In this case, we spray a pattern on there of white and black. These are completely non-uniform pattern. From the pattern, we can use the two cameras and the projection of light to ascertain the change, and from that we can work out the mechanical properties. So we can look at strain, Young's modulus, and so on. Where it's needs to be a little bit different, this is a digital image correlation. So in this case, we're using these marker dots or reference points. And this is 3D tracking live what's happening, in this case, the door slam test. So it's measuring in 3D, it's measuring hundreds of thousands of times a second to track the position of this. And from this, you can see, I use it later in the slides, a picture paints 1,000 words. And that's really what the industry requires now, how we are helping to change this by really pushing things forward at a fast rate. And software. So the software, I will actually just show the software real quickly before the end of the session. The software is the jewel in the crown, let's say. This is what brings everything together. So the founders were two guys doing PhDs. It kind of stemmed from the 3D testing where they were checking for for displacement and movement as part of their thesis. That built then the 3D scanning technology, but they needed help then to put this together. So the three founders are two from the hardware side and one from the software side, and he's built this team and this software that really brings everything together and helps to give the designer, the manufacturing engineer, really what they need from their products. Okay, so as we've outlined, this is the full solution software through the sensor systems, machine and automation, which has been really customer driven over the years to meet the emerging needs and to replace some of the more legacy systems. Okay, and I guess as you'd probably expect, this covers all topics and all industries from the plastics, consumer goods, everything from your iPhone to your Samsung to your Bosch power drill. More often than not, there will have been some sort of GOM system in the product evolution, whether that is for the design and validation phase, or whether that's for the volume production measurement of these solutions. Certainly, in the automotive sector, this has been and continues to be a real step change, where optical metrology is becoming very much the standard. My focus being aerospace, this is something that I'm really pushing quite hard to make people see the benefits and to see what that brings. And quite clearly, actually, the research and universities, particularly the testing equipment, is really important for analysis. Actually, Dr. Carl Dern, he did text me the other week saying he'd been part of a purchase or something to assist his students and his projects, which was really nice to hear, actually, that playing a significant role for him as well. Globally, yeah, we're really global now. We're actually part of the ZEISS organization as well. So if you're familiar with the Carl Zeiss for CMMs, for optics, and so on, we went through a merger and acquisition sometime last year, which really expands the network somewhat more. But yeah, some 1,200 metrologists around the globe, 8 GOM group companies, and we use a partner network called the GOM Certified Partner, who are resellers and support networks around the globe. And we have headquarters in Germany. That's who I work for. Although I'm home office, I tend to spend maybe 1 to 2 weeks a month over there working with our product development teams and sales organization. And then we have 2 regions, one in Shanghai, one in Charlotte, which support better across the time zone. So this is one area that is really pushed the development, particularly for manufacturing. Manufacturing really demanding faster time to market, faster inspection, more complete inspection, and the scan box has helped to do that. You can see it goes from the really quite small, as we started with, to the very quite big whole body parts. This is all fully automated standard solution now that literally you can buy, and in the case of these top 4, within just a couple of months you can have one of these installed. These will run fully autonomously. They will run, as we would say, lights out, so you can literally walk away, have the part measured, come back sometime later, and the results are there for you to do whatever you need. being pushed even further, we then have even more kind of autonomous systems. We have companies that have like AGVs to load these and unload these, so they're even more integral to the process. And these really are being used in a full scale, high volume production cells. So, you know, I gave the theme of why this is changing design and manufacture. And I guess as you get a feel, and with a kind of half-hour topic, it's hard to go into all of the details, but you can probably feel and get a feeling, at least that, as I said earlier, a picture paints 1,000 words. Not everyone is ready for 3D immediately, but what we do well is we do the conventional inspection very well here. So if you're looking for normal GD&T on, say, a hole or a surface or whatever, you can report this as you would today with any other kind of device. So we kind of maintain a status quo. But for those that are a bit more advancing, you know, I would say with scholars like myself back in the Rolls-Royce days, you can see then the kind of power, the ability then that you have there afterwards. So for in a design, you know, the buzzword at the minute, I guess, is digital twin. And you really get this, you know, you really get a complete 3D representation of your product. Um, if this is something like this Bosch handle here, then for the designer, she can understand how this fits together correctly. They can understand warpage, change, and so on. If this was something like a turbine blade or a blisk from a gas turbine engine, you could re-evaluate this. So you know you have the real data to feed back into your analysis tool. At the end of the day, we generate a mesh. You know, mesh is the driver of softwares like ANSYS and aerothermal packages where they are looking and using this type of data. You can really, you know, feed that back into the softwares and confirm assumptions. You know, validate assumptions. What is actually happening with the product? Is it as we predicted? What's the difference? Why is it different? And you have that 3D data that enables you to do this in a real nice way. Probably overlooking the fact that you know a lot of association with optical metrology is that it's quite rough. It's maybe approximate. It's not actually high resolution. But we've demonstrated time and time again, particularly for aerospace customers that are very demanding on the accuracy levels, that we really do have micron level, you know, single figure micron um, resolution and also accuracy. You know, we're always having to do benchmark tests, always doing it to traditional techniques like CMMs, and consistently able to achieve these results. One last thing, maybe for a designer, we've incorporated in recent software releases augmented reality. It's quite a driver. We have lots of buzzwords like Industry 4, digital twin, you know, and we're really there. We're really ready for this. I wouldn't sit here and profess, at least to this audience, that we are there now in terms of are people really actively using this, or is it still conceptual and people still just kind of talking about it? I think it's more at that phase right now. But in this case, for augmented reality, you can see this is the actual car body in the background. And what you do there, you take a tablet device with the software on, with a webcam, and you activate the software. You point it at the product after you've measured it, obviously, and you can see the inspection plan overlaid on your tablet onto the car. So if you've got a major defect that you want to go and have a look at, or a design function you want to go and look at physically, what does that look like? Where is it? Where's the location? You can go and physically do this with something like augmented reality. On the manufacturing side, this is where we see, I would say, most users, at least in my industry, where the combination of high quality data, being able to inspect things as you've always done, to a drawing, to a print, where you're looking to validate GD&T, and in most cases doing it in a fraction of the time compared to traditional techniques, and in an autonomous way. This is really where we're seeing that kind of change in the manufacturing sector. It's also the manufacturing sector that has forced, more often than not, by the pace required for the time to market with products like cars, like consumer goods, that have really pushed on the technology in other ways. So take digital assembly. So we saw from the image here that these individual parts of the car, for example, here, could be measured in the corners of the globe, brought together at a head office somewhere, or in any office, built together like the real car. So in the economy and the way we are today, this is a really effective and efficient, and also quite green way of being able to evaluate what the final product will look like, to help resolve any problems along the way. So this example is, like I say, it's bringing the bonnet, the doors to the body, positioning them, and you can also then do virtual assembly of this, and you can look at tolerance stack, you can look at datum systems, and how this can be improved. It combines traditional and modern techniques for inspection. So it's an inspection tool, and you can do all of the traditional GD&T, but where we are moving more generally is in this kind of 3D world, and being able to look at, in this case, deviations on the car. In this case, you can see this very visual, very 3D comparison to CAD or to master parts or whatever. We're extremely fast. In most benchmarks we would normally be at least sort of half of the time of a traditional technique. Traditional to us normally means CMM, so where you're seeing the probes moving around and probing this stuff. To do the equivalent inspection in all kind of benchmarks would be in the order of 50% of the time to do the measurement. And obviously with this technology, then you can do the existing measurement, but you get more. You get all of this 3D data that some of it does still get wasted, but it's there. It's future proof. So when things start moving more progressively in this way and being a little less about the talk, and this really is future proofing businesses. Certain key companies work with us a bit more. They are using the 3D data and they want to do a little bit more. So in this case, this is what we call surface defect detection. So in this type of scenario here, this is a comparison to CAD. There's some quite gross errors here, and what you can't see is maybe some little imperfections that are just getting washed out by the surface. Surface defect is really looking for dents, nicks, scratches, bumps that are part of the product of the manufacturing process, the stamping, or work holding, work processing process. These are really inherent in those processes, and you can do categorization, worst to acceptable, count them, rank them, look at them in size, shape, and so on. This is a really advancing where we're going. And then the last one, this is really recent. We're going to present this at our major exhibition in May this year, called virtual clamping. So this left-hand image is looking at the this stamped, this pressed sheet metal part here in its free state. So it's just measured in the free state, and you can see that in this area, sorry, there's areas that are just kind of the springing effect of the sheet metal component. What we've built in is an engine now within the software that can compute clamping. So in the real world, this would go into a fixture. It would be clamped down on the 3, 4, 5 positions, which basically simulate where this would be and be adjoined in the car, for example. What we're able to do is to do that virtually, so we can simulate the points, we can simulate the forces that would be applied on the clamps, and although measuring it in a free state, we can simulate then what that looks like in the clamped condition. Why would we do that? Well, the customers have kind of pushed us that way, and you also start to really become more efficient and reduce costs significantly in the manufacturing processes. For example, the fixturing to clamp these in position, they will need calibrating, they will need manufacturing, designing, they will wear over time, and these really are how we are, let's say, transforming the way in which manufacture is looked at and viewed in the future. So yeah, really really advancing the technology. So if I just really quickly come out, conscious of the time here, but those that came to my year as president will have come to GOM UK in Coventry, and you will have remembered maybe that we measured the president's medal here. So this isn't a card. This is literally the mesh of the medal. So if we're looking at what is the kind of resolution, I've put the mesh structure here, which you can literally check out Sir Joseph's beard, essentially as it is produced from the Royal Mint. Okay, and from this we can, as I kind of outlined, we can do different types of inspections. We can, I did prepare a couple already. So I looked at, how big this is, and I noticed that this was just over 57 millimeters. Thought that was a peculiar number, and then I realised, actually, it's about 2¼ inches, which would make more sense, and perhaps stem from how long just we've been manufacturing these types of parts. Also looked at things like cylindricity, how round the outside of this is. I would have maybe expected this to be a bit more, but this particular coin has been around a lot and been used for some time. And then let's say, the flatness, just looking at the flat or not so flat surface around the print here, and what that means to us, and just where the high spots are here, and a range of about 0.3 millimeters across that surface. So really, so I guess something more relevant for us, but just to give you a feel for what this can be used for. As well as the new and the future, you do find that this is also used a lot in reverse engineering applications as well, where parts are measured without drawing, without CAD and so on, and then CAD is recreated. This is a good way in which you can kind of make a product reborn again. You can really bring something that evolved back to life by scanning it in a nice way and then bringing it into the modern day. Okay. Okay, so I mean, just looking at the time, it's been about 35, 40 minutes of me rambling on. In terms of a high level feel for what it is, I appreciate it. It's also a lot of corporate slides, but they also, really help to get the message across that this is, something very real, that's being used day in, day out by manufacturing companies, design companies, consumer goods, aerospace, and everything in between. So that's a real quick overview. Take questions in a second, but just take the opportunity really quickly. If you've not already seen or received email in the last 24 hours about the commemorative meeting, this will be in the Arme Key again, in the library at Birdcage Walk. This has been secured just recently for the 20th of March. So not long to get your responses in, to pay for the meal, arrange transport and so on. But on behalf of the committee and everyone at the society, would really welcome everybody to get to this event. Okay, so at this point, if there are any questions, I'll just take one. Yeah, shoot, Sam. So, question on micron level resolution. Can it do surface finish? Surface finish at the moment, no. We can't do surface finish, but we can measure two single microns. So, in terms of studies that I've done with aerospace products, we would get to correlation studies to an independent system where we would measure to around 1, 2, or 3 microns, getting exactly the same result with an independent system. Surface finish hasn't yet been built into the software. Another question, Sam, or you? Okay, a couple of years ago, probably outdated information, but I heard the optical measurements aren't traceable to national standards. It's important to no, it's not. It's not true that the optical measurement isn't traceable. It's true that there's not necessarily international standards that would validate optical systems, but it is entirely possible. So in particular for these types of technologies, we use artifacts in the process which basically set the system. So for basically like the scaling of the measurement data. So in the scaling, the artifact, this does go back through traceable labs. We do this by measuring a series of hole patterns and looking at the distances between these, which we use in the algorithms to compute the 3D data, and this is how we are assured that it's okay. So the artifacts themselves go through the traceability loop. So we use a calibration panel. This gets measured by external parties to check the spacing, and we use this data in our algorithms. We also then have artifacts, so ball bars, like maybe equivalent to an ISO 10360 for a CMM, where we measure some spheres. Again, it's a known artifact that's been sent away to a lab. We use these to ascertain the size, the shape, the profile, the distances between them. Again, this is the way in which we are traceable. Specifically for aerospace, there is a set of audit criteria. It's handled by the PRI, Performance Review Institute, under the headline NADCAP. So those that are from aerospace will probably be familiar with NADCAP for as a standard for things like welding, heat treatment, and so on, where this is like an agreed accreditation that you can achieve. There is a specific checklist actually for use of 3D metrology, and this is yeah, fully accredited, bought into by the aerospace prime companies like Rolls-Royce, like Boeing, and so on, as the standard to achieve. So so yeah, there is an ISO standard 10360-8, I think, that will come into force for this technology. But even in lieu of that, it's completely traceable in its current form. Sorry for the long rambled answer there, Sam. Okay, cool, super. Okay, so I've pretty much hit the mark there, I guess, of about 45 minutes. So yeah, thank you for your time. I will stop the presentation, stop the recording, and catch up with you again soon. Thanks very much.